Folks, so this is where I left you. I left you with this idea of a polarimeter and what a polarimeter does. Oh, how sweet. We have one in our laboratory. You probably will do a lab experiment using the polarimeter so that way you can at least see how this thing operates. But it's a very simple device that's very expensive. It only requires a light bulb. The light bulb provides wavelengths or light in all directions. That requires a polarizer to streamline this down to one direction only. That one direction goes into what we call the polarimeter tube, and that polarimeter tube will hold our compound. That compound will then decide not to turn it at all, and if so, that is an achiral compound, or it will turn light. And if it does, that means there is a chiral center at play. So that chirality is going to lead to rotation of light, and we can measure the rotation of light by basically matching it up from the originated spot or the origin. So a couple of words I want to bring into the discussion here. If you paid attention in the last video, you noticed that I designated right-handed and left-handed with a positive and a negative. So this is moving it right-handed, this is moving it left-handed. The actual light, not the molecule, but the rotation of the light. However, as you can imagine, some people do not like the positive and the negative. Don't ask me why. Maybe very early on they decided it wasn't going to work for them for some reason whatsoever. Positive and negative is what we use mainly in the organic chemistry laboratory or in the chemistry environment. But there's also another designation. There's another word that we can assign to the rotation of light. Bottom line, that's what it is. So, what words do we use? We need to expand our organic vocabulary. And with this are two words, one called dextro and the other one called levo. And then they add the word rotatory on the end, R-O-T-A-T-O-R-Y. R-O-T-A-T-O-R-Y. I got ahead of myself. So dextrorotatory and levorotatory. Well, D for dextrorotatory and L for levorotatory are also two of the words that we can bring in to the picture. Now, we are going to introduce maybe D or L. It depends on how good I feel, right? If I want to travel down this path, we can designate D's and L's for another reason in the lab. But these are two terms other than just right or left that we can use when we describe polarimetry activity. Dextrorotatory, levorotatory. Rotate, you see the word rotate, and dextro means right, and levo means left. Now, something else that's going to happen with the polarimeter. Remember, I keep talking about this light source. Okay. So, normal light really represents, if you want to imagine, Roy G. Biv. Again, general chemistry stuff right here. Red, orange, yellow, green, blue, indigo, violet. All of the colors of the rainbow are included in just natural light. Well, that's a lot of variables, folks. That's a lot of stuff going on. We need to streamline this down a little bit more. So what we decide to do in the polarimeter is only focus on one wavelength, not all the wavelengths of the electromagnetic spectrum. That one wavelength is 589 nanometers. This is going to be provided by a light source, a lamp, that we are going to call the sodium D lamp, or the sodium D line. And folks, quite honestly, back in the day when the electromagnetic spectrum was getting discovered, and when they were talking about red, orange, yellow, green, blue, indigo, violet, as well as UV and infrared and all of these other components of the spectrum, you know, we go into an area of the visible. 589 is part of that visible spectrum, so we can actually see a color associated with this. And sodium, like all the other metals off the periodic table, give off a certain electromagnetic spectrum that we call atomic emission. They are lines that are given off, colored lines if you want to think of them that way, that we can measure with another instrument called atomic absorption. That is abbreviated as AA. So sodium gives off a certain wavelength, and lithium gives off a certain wavelength, and copper gives off certain wavelengths, and magnesium and iron, all of the metals, especially the transitions, the valley in the middle, give off this emitted light that we can pick up from an instrument. Well, a lot of people ask what the D represents with sodium D. Nothing. It doesn't really mean anything at all. Back in the day, they used to provide very shortcut directions, okay, when it concerns electromagnetic spectrum. And they would assign different areas. Well, this is going to be A, and this is going to be B. This is going to be C, and this is going to be D, and this is going to be E, so forth. So sodium just so happened to fall in the D range. That's kind of how all of this got started. So that's why we call this the sodium D line. It gives us an idea of where at on the electromagnetic spectrum that we're talking about. And again, it started with the letters of the alphabet. So most polarimeters that are used today in a lab are going to be using a sodium lamp. And we look at the sodium D line, and that sodium D line is 589 nanometers. So what this allows us to do is we have one wavelength now. That's it. It eliminates another variable. So no longer are we talking about just any old light bulb that gets plugged into the polarimeter. That's not going to work for us. A normal light going into the polarimeter cell, too many things going on. Too much. Alphabet soup. Right? We need to clean up the alphabet soup, and in this case, we only need to pick out all of the D's of the letters. That's it. So once we do that, well, we have a very cleaner bowl. So therefore, cleaner calculations and measurements can happen. And that's the whole purpose of using a sodium D lamp. It streamlines this down once again to one wavelength and one wavelength only, and that's 589 nanometers. So, now that we know that, there's more to the story. What is it? Well, here's an image. And what you're seeing in this image is a schematic, I guess, if you want to call it that, of a polarimeter. So here's our light source. But guys, we know what our light source is now, right? We know that this is a sodium D lamp. And we pick that because one wavelength only is chosen. And a wave, of course, is this up and down motion that begins to happen. And the closer these are together, the more powerful that wave is going to be and the more energy that it's going to give you. So that is what we call the wavelength. That wavelength is going to be abbreviated with a lambda. So 589 nanometers is the wavelength for the sodium D lamp. That light energy comes in and it goes through a polarizer. And the purpose of the polarizer, once more, is to choose only one direction, and that is it. It doesn't allow everything to come through. That one directional light hits what we call the polarimeter cell. And there's molecules in here. There's a solution in here. An organic compound is in here. And when it goes through this polarimeter cell, there's a chance that the light would not be disturbed. Look at this. It still goes up and down, just like it did when it first came in. If this is what happens in a polarimeter, there is no rotation. There is no rotation of that light. So we have an achiral compound that is inside of that polarimeter cell. That's what achiral compounds do. They do not rotate light at all, period. They don't do it. However, if we have a compound that has a chiral center, like a chiral carbon, then this will rotate light, and we have a set of enantiomers that we have to go through. Well, here's the light source, just like before. Here's all directions. The polarizer picks one direction only to allow it to go through, up and down. That up and down orientation goes into the polarimeter cell in the very beginning. And as you can see, the molecule that's on the inside of the cell, it begins to turn the light. And you see that arrow turning and turning and turning and turning, and then eventually it ends up with this direction here at the very end. This light has been rotated. So if I look at the end of the polarimeter and I use my eyeball to see if I can see any light, I would not see any light coming through. I would have to take that rotator plate and I would have to rotate that plate, left hand or right hand, until I see light escaping. And then I read how much I've turned. That's the old school way of using a polarimeter. We've got better equipment than that, though. I mean, you know, we like to be a little bit braggy. In the chemical technology department, at least, we like to be a little bit braggy about the equipment that we have. We have a polarimeter that does everything for me. I just got to put the solution in the polarimeter cell, and then that's it, folks. Away I go. So that's good, right? It takes the guesswork out of it. That's why we do that. If we have a compound that is rotating light like this, again, we know that we have a chiral compound. And more than that, we know that this thing is what we call optically active. Because it's rotating something. It's rotating the optics of the light that I'm sending through. Okay. Now, a couple of more variables that we need to talk about. What else can go on in this polarimeter cell? Well, there's one more thing, two more things actually, that we need to focus on. One is the cell. Look at this. As you can imagine, this polarimeter cell could be made in different lengths. Okay, that's going to be pretty important. Because if I have a longer cell, there's more stuff on the inside. If there's more stuff on the inside, it's going to rotate that light even more, isn't it? Because I have more of it. So the length of the cell is a variable that we want to control. Very important. The other thing that we also need to pay attention to is the concentration of the solution that I put into the cell. Most of the time these are going to be liquids. These liquids will have to be in a solvent. Well, how strong do I make it? Can I just put whatever I want to put in there? No, you can't do that. We have to be very specific on the concentration that we are putting in that polarimeter cell, because the more concentrated it is, the more stuff on the inside, the more stuff on the inside, the more it rotates, and that is a variable that affects the readout. So all of these things can be changed. And this is where a problem happens. We have to make sure that we're comparing apples to apples, folks. Okay? When we put compounds in a polarimeter, and my lab does it, and your lab does it, and someone else's lab does it, we have to make sure that we're talking about the same thing. We have to make sure we're going to compare apples to apples, and we're doing it the same way. So two of the things that can be different that we need to correct for is the length of the polarimeter cell, and we abbreviate this with an L. The other thing is the concentration of the sample that I'm putting in that cell. And we abbreviate this with a C. These two are variables that will go into an equation. Oh no, an equation, that means there's going to be math. Yeah, that's right, there's going to be math. And these two things play a factor in the readout of the machine. Well, this machine will give me a readout. That's great. And we're going to call this alpha. That little fish symbol, Greek letter, alpha. Okay, well, alpha means something. That's fine. It represents a degree, a rotation. But if I want to assign a proper term for that, it's going to be called an observed rotation. Why? Because you observed it. You put the compound in the polarimeter, you ran the polarimeter, you read a number, you wrote down that number. That is what you observed in the lab. So this alpha is called an observed rotation. And the observed rotation depends on the length of the polarimeter cell, and it also depends on the concentration of the polarimeter cell, of what's on the inside. We need to take all of these variables into consideration, and we report what we call bracket alpha. That means something different. What this means is a specific rotation. It's specific to that compound that we're running, but it's also very specific to a predetermined polarimeter cell length and a predetermined concentration as well. This allows me, my lab, to pick whatever length of tube that we want and to run whatever concentration that we want to run and plug it into an equation and correct for those values so I can get a specific rotation for that compound. And the specific rotation, those are the numbers that are going to be involved in the textbooks. Those are going to be the values that are going to be in reference books. These reference books are going to be things like something that we call the Merck Index. Merck Pharmaceutical Company folks years and years and years and years and years ago decided they could improve their workflow before the time of the internet if they come up with a book with all of the common properties of compounds that they used on the inside. It was so popular that they began to sell it. And this book is still in existence. It still gets updated every other year or so. We still get a new edition of the Merck Index that comes out. That's how all of this got started. In that Merck Index are various compounds. I looked them up. Those compounds are going to tell me everything from boiling point and formula weight, density values, refractive index values, and also specific rotations if applicable. What do you think people did before the day of the internet? I mean, before Wikipedia happened. What do you think people actually had to do? They had to use reference books. And we still have those today. We still use them. Another reference book that you might find specific rotation in is the CRC, the Chemistry and Physics Handbook. That stood for the Chemical Rubber Company. The CRC was another company, basically book, that did something similar to what the Merck did. And the CRC normally has different things than what you can't find in the Merck or vice versa. We also have those textbooks and reference books in our laboratories as well that students use. No big deal. But these textbooks or reference books has optical activity information in it. And this is going to be regarded as specific rotation. because we have to correct for the polarimeter cells that you use in the lab and the concentrations that you will use in the lab to get the observed rotations with. And all of this has to come together in an equation. And folks, this is what the equation looks like. Yep, there's going to be a little bit of math here. I know. I lied. I told you maybe in the beginning of the semester that there's going to be hardly any math. Oh, I said hardly, didn't I? There's going to be a little math, and this is our first encounter of it, really, of an equation. The bracket alpha, this is your specific rotation. This specific rotation also is temperature dependent, and that's what you're seeing the T up here at the top is going to represent. So the specific rotation in a textbook will typically have a number here, and this number will let you know what temperature that solution needs to be. Typically, it's like 20 or 25, room temperature. This is also going to be dependent on the type of lamp that you use for the polarimeter. That's why you see the lambda here, and we now know that that lambda represents wavelength, and this wavelength is the sodium D line. Sometimes they will write D there, and that's what that means, sodium D. That's the lamp that's involved. So specific rotation is equal to the observed rotation, what you see in a lab with your measurement, divided by the length of the polarimeter cell times the concentration of the solution that's inside of the polarimeter cell. This concentration in a laboratory, concentrations can come to us in many different forms. Molarity is one of them. Normality is another one of them when it comes to acids and bases. I could get volume percent. I could get mass percent. I could get part per millions, part per billions. I mean, the list of concentrations go on, folks. They lie to you again in general chemistry and pretend like molarity is the way to be. But it's not. That's a fib. That's a lie. So what concentration do we use for this equation? Well, this concentration needs to be in terms of grams per milliliter. That's the unit that we need to use in order for this equation to work. Grams per mil. So folks, this is the equation used to calculate specific rotation. We're going to have to do some examples of these, right? I mean, they're going to give us some word problems, and they're going to say, you made this solution, you put it in a cell tube, this is the length of the cell tube, you put it in the polarimeter, you got to read out of this what is the specific rotation of that compound. Those are the simplest and easiest questions that come along with the polarimeter exercise. The length of the tube is also important. However, the unit is as important. And the unit is in terms of decimeter, not meter. A meter is about the distance between the floor to your waist. That's a meter. Well, decimeter is a tenth. That's the decade, a tenth, 10 years. So it's a tenth of that length. We do not use 1 decimeter tubes in our polarimeter cell. We could, but it's not really needed. In our laboratory, we use 0.5s. They're 0.5 decimeters. And that's the value that we will use in our lab when we do a polarimeter lab with them. But decimeter is the unit that we have to use in order for this equation to work. So concentration unit has to match, and the length of the polarimeter cell has to match. Here's an example of some specific rotations. What you're seeing up here, mainly medical, or at least drug related. Aspirin is a drug just like cocaine is a drug. Okay? One a doctor prescribes and the other one you get thrown in jail. But they're both drugs. They both make you change when you take them. Well, why is one accepted and the other one's not? Well, there's a discussion that needs to be had with that. But what you see on the screen right now, up at the top is cholesterol. It's optically active. It rotates light left-handed. It's levorotatory because it's negative 31.5. And then down at the bottom, sucrose, which is table sugar. All right, well, that sucrose, granulated sugar, is optically active. It has a rotation of positive 66.5, which means that that is dextrorotatory. And if you look at these numbers, they can go very high. I mean, we're in hundreds, right? Testosterone, dextrorotatory, 109. I can go negatives that far as well. Specific rotations can also be very tiny numbers. Look at cocaine. That's negative 16 up on the screen. So it rotates light left-handed. It's levorotatory. And its specific rotation is negative 16. But folks, if you see 0 on this list, that means it is not optically active. It's not optically active. There's two ways that we can get 0 on that chart. Number one, you just don't have a chiral compound, right? No chirality. That's the first way you can get it. The second way that you can get it is a mixture. What if you had two versions of a compound, the same compound, and some rotate it left-handed and some rotate it right-handed? And what if this was a 50-50 split? One does not outweigh the other. Well, as you can imagine, half of the substance will rotate it right, half of the substance will rotate it left, and if I mix it together and I do an overall calculation, they cancel each other out, don't they? That's another way that I could get 0 for optically active. They're canceling each other out. They're working against each other when it concerns rotation of light. Once more, I also want you to keep in mind that R and S has nothing to do with positive or negative. Nothing. So here's 2-methyl-1-butanol. This is the R form. How can we know? Carbon, 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 you go next. O, carbon, nothing. This is rank 1, this is rank 2, this is rank 3, and there's our rotation. That rotation is going to be an R. That is where that letter comes from. Has nothing to do with light. We make a solution, we put that solution in the polarimeter, we get a readout. That readout is a positive piece. It just so happens to be positive here. Just so happens to be positive. Here's the specific rotation. Sodium D lamp at 20 degrees Celsius at room temperature. I get a positive dextrorotatory at 5.75. Well, if I look at the S molecule is here, up here at the top of 2-methyl-1-butanol. We put that into a polarimeter, and folks, we end up getting a negative here. A negative 5.75. It rotates light left-handed, or levorotatory. R and S has nothing to do with positive and negative. I can't say that enough because it's a common mistake that people always have in the world of organic chemistry. So I'm going to leave you with an example problem. We'll work on this when we come back. But it says the observed rotation of 2 grams of a compound in 50 mils of solution in a polarimeter tube 50 centimeters long is 13.4 degrees. What is the specific rotation? So this is what I want you to do. I want you to try this problem before you hit play on the next video and see if you can come up with the right answer. You know the equation. We just wrote it down. You know what the variables represent. You know what units have to go into those variables. So all of a sudden, we need concentration. Well, we don't have concentration, but we do have 2 grams that are in 50 mils. Maybe I can use that to calculate. We also have the length of the tube. Well, the length of the tube, though, the problem here is that it has to be in decimeter, and this problem gives it to me in centimeter. I'm going to have to be able to go through, and I'm going to have to be able to convert centimeter into decimeter, because that's the number that I need for the equation. And then the observed rotation, what I saw when I ran this was 13.4. So I have all the pieces of that equation that's needed in order to solve for specific rotation. So see if you can do it. And then press play, come back, check your answer, and we'll go from there. Good luck.